Okay, so last time we talked about power series, and you saw we saw this this theorem that, I mean, we didn't prove it. You'll see more of it in the exercise session. But we saw this theorem that every power series has a radius of convergence. That inside that, right? So for every power series, we have, let's say, right? So if we have something like ANZN for some sequence AN, right? And we have the complex numbers where this is 0, there's some sort of critical circle R, such that inside of R, things are absolutely convergent. And outside of R, they diverge, right? So here things diverge. Here they're not only converge, but they're absolutely convergent. Okay? And if you want it to be uniformly convergent, all you have to do is draw another circle inside this one, and then you're sure that they uniformly converge, right? The issue being that the speed of convergence can sort of get slower and slower as we go towards the circle, right? And then we saw, well, or we didn't see, I guess, but the theorem said nothing about what happens in the circle, right? And actually, there were some quite interesting discussions on the forum about examples where, you know, it's quite non-trivial to see what's happening at the radius of convergence, right? Because at the radius of convergence, you could have all sorts of behavior happening, and the convergence might depend on where you are in the circle and all this. And for now, we're not going to talk a lot about convergence on the circle. Okay, so now one thing that, you know, should be familiar to many of you, but let's say that, right? But this highlights another importance of the series. Let's say that I have a function. Right, we also saw that inside the radius of convergence, then functions are differentiable. Right, and in fact, the derivative from the viewpoint of complex analysis, right, the complex derivative is just differentiating the series as a polynomial term by term. Right, so let's say that we have a power series like this. And so on and so forth, right? Let's say a term, let's put one here, ANZ to the n. Right, then if we take the derivative of this, right, what do we get? Right, as long as everything is convergent, let's say that I have that this is equal to, right, this is equal in some neighborhood around z. We'll talk a little bit more about point set topology today, so, you know, it'll be more clear what I mean by neighborhoods and all this. I'm assuming you saw a lot of this in analysis, but we'll revisit a lot of this, right? So taking the derivative, I just do it term by term, right? So I get a1 from here, then I get 2a2z, right, and so on and so forth. And what I get here is just n a(n) z to the n minus 1 plus and so on. Right, and, you know, I can differentiate again, right? Because now we saw also in that theorem that, you know, when I take the derivative, the power series will have the radius of convergence will be the same, right? So inside the circle, it will converge just the same, right? So now if I were to do this again, what do I get? I get this term goes away. I get 2a2, right? Now I have, you know, the a3 had a 3, and now has a z squared, so there's another 2 that goes by. So you have 2 times 3, right, 6. I mean, no need to write 6. a3z plus, and now what does this term in general look like? N minus 1, n a(n) z to the n minus 2. Right? And in fact, right, it's not so hard to see that at the kth derivative, right, I'm sure you've seen this in real analysis. You just have to work it out. This is just, you get k factorial ak, right? Because now if I were to differentiate again, I would get 2 times 3, right? So the third derivative would be 3 factorial and plus, right, k plus 1 factorial over 1 factorial a k plus 1 z plus, right, and just this ad infinitum, right? So over 2 factorial of a k plus 2 z squared, and so on and so forth. Okay, but so what does this tell us? This tells us that if I were to now take z equals 0, right? If I were to do z equals 0, right, then all these terms would go away, right? And in particular, this means that if I work out, right, this right, I have this power series that now should still, right, I do this a finite number of times, it should still converge in the same radius of convergence. And now I can take just z equals 0, and what do I get? I get that the kth derivative at 0 is equal to what? Okay, so this becomes 0, 0, all these terms get 0, so only this term survives. And so I have k factorial ak. So in particular, what this means, right, I can now swap things around, and I get that ak is equal to 1 over k factorial f k of 0, right? And so in particular, it means that if f has a power series, which I have not shown that all functions have a power series or anything like this, but if f has a power series, then it needs to be given by, right, the coefficients are given by the derivatives, right? So in particular, if f is a power series, then we know exactly what the coefficients are, right? They are just, right, f0, k plus, right, I guess 1 over 1 factorial. I mean, 1 factorial isn't anything, but f, oh, this is, okay. 1 derivative plus 1 over 2 factorial, oh, z, of course. 1 over 2 factorial second derivative, z square, and so on and so forth, where the nth term will just be, or let's say the kth term, to keep with the same notation, f k at 0 z to the k, right? And this is what's known, right? And so this is known as the Taylor, right? We know this as Taylor series, or more general Taylor-Maclaurin series. Okay, so for now, we haven't showed that functions necessarily have a series. All we showed is if a function is given by a power series, right, then the power series needs to be its Taylor-Maclaurin series, right? And this is sort of elementary, right? If a function is written by a power series, then we know that these coefficients need to correspond to certain derivatives, right? I'm sure you've seen versions of this in real analysis. It's exactly the same thing that's at play here. Okay. And so what we'll see later is that analytic functions that are analytic in a region, or in a, I'll define what a region is, but in a neighborhood, or even say everywhere, they will always have series, right? They will always have a Taylor-Maclaurin series, but we haven't yet proven this, right? And sort of the interesting thing, and this will come maybe a week or 2 weeks from now, is that this amount of regularity that we're going to prove out of complex functions, right? Because, right, we're about to prove later in the course that actually complex functions are smooth enough, right, that you can take derivatives in, say, an open set, something like this, then, in fact, they will always be given by its series, right, which is definitely not the case over the reals, right? A function being differentiable and being analytic is different over the reals. But one of the incredible things is that the way that we'll prove sort of most of these theorems about analytic functions in a complex plane, about differentiable functions, is via complex integration. So we're going to develop the notion of integration over the complex numbers, and particularly integration over curves and so on in the complex plane. And this is going to be the main tool to prove all these statements about complex functions that a priori have nothing to do with integration, right? And this is sort of one of the magical things that I think will be more clear as we go, as we go forward. Okay, and I mean, if you've seen some differential equations, not so different from how in differential equations, oftentimes when you want to prove things about your solutions, you set up your solution as some kind of integral or something else in the physical problem, in the problem that you're trying to study, and then that allows you to prove a lot of regularity, and in a way, that's what's going to happen here. But okay, if you've never seen those kinds of techniques, it doesn't matter, we're going to do this all the way from the beginning. maybe one way that, even if you haven't seen things of this style, maybe one way of intuitively understand why something like this might help, okay? It's not proving anything, just some intuition, is let's say that you're studying the steady state of some type of diffusion, right? You have some, chemical in the water that's diffusing, or some heat or something like this that's very diffusive. Then it makes sense that in some kind of steady state, you expect that the temperature or the concentration at a point should be somehow some average of the things around, right? I mean, you expect, because if it was, if the temperature at a point was sort of smaller than the average of the things around, you'd expect maybe it'd get hotter and the other way would get colder, right? So there should be some equation of this type, and indeed there are equations of this type. And so the value at a point is sort of, you can maybe, easily believe that it will relate to some kind of integral of the points around, right? At least if you have some kind of steady state of, say, a diffusive process or temperature just evolving. And then once you get that, it's kind of clear, because you're taking an integral of something, maybe then you can differentiate better, or you can prove regularity conditions about it, and that these formulas might be very useful. And you would imagine that, for example, in the steady state, temperature shouldn't have any kind of kink or non-smoothness, right? Because if something was sort of very hot in one place, very cold in the other, it should smoothen out. And this is sort of what's play in here, or will be in play, right? Because we even saw that analytic functions will be harmonic, right? And so this will force them a lot of regularity, essentially for the same intuitive reason. If you like to think in terms of more physical terms, this is maybe a good thing to keep in mind. Okay, so now we're ready to talk about exponential and trigonometric functions. This is about time. And then we'll go and do some point set topology, maybe in the second half. Okay. Okay, so exponential and trigonometric functions. Okay, so basically what we'll argue is that the exponential y times a vector x is equal to, right, this is known as Euler's formula. Right, is one of the nicest, it's one of the most, I think, surprising things in complex analysis, right? And we'll see why this is the case. I mean, yeah, so if you go and look, okay, I guess first of all, right, exponentials and trigonometric functions, they look like they have nothing to do with each other, right? So it's sort of surprising that this should be the case. Right? Now, if there's a few things already that maybe make this not be as surprising, right? Let's say that I think of x as an angle, right? And what this is saying is, if I take exponential of I to an angle, basically I get a point on the unit circle that is just with that angle, right? Because if I take, but we'll see why that's the case. Okay? If I take some angle theta, then basically this point is cosine theta I sine theta. And so what I'm saying is that this is e to the I theta. Right, but now we know that the exponential, when we multiply two exponentials, the arguments inside add, right? And we saw this earlier, that if we multiply two complex numbers, then the angle added, right? Which felt very strange. And in fact, the way we proved it was we took this, something like this times something this with another point y, and we saw that this was the same thing as replacing, right, as doing cosine of x plus y and sine x plus y. But now it becomes completely obvious, right? Because the exponential, at least over the real, satisfies that the product of the exponentials is the exponential of the sum, right? So all this stuff starts being a bit more transparent. Okay, and there's many ways of trying to. So if you look in, like, I don't know, the references that are on Moodle or on the page description, and you look at like the 4 or 5 top books, I think probably every single one, or almost every single one, shows this in a different way. And what I mean by that is that you can you have to define what the what the exponential is over the complex numbers, and you also have to define what cosine and sine are over the complex numbers. And so you can just define the exponential to be this and then prove properties of it. You can define the exponential to be its Taylor series and then try to prove this. You can do all sorts of things, right? And so one nice approach, right, that's taken by the main reference that we're using is you can just define it with respect to the differential equation, right? The x should be the function, should be the solution, should be a solution of, right, f prime, or let's say E of z, right? The exponential of z should be a solution of the equation where if I have, right, where the derivative is the same thing as the function itself, right? And let's say we would like that f of 0 is 1, right? Because we know that E of 0 is 1, right? And now it's, right, and now, okay, let's say that you define it this way. Now you can write its Taylor series, right? If you write, say, if you believe that it has a Taylor series, then you can write it as, right, this part of trying to define the exponential is a little tautological because there's so many ways of defining it, and then you can just prove. You define it one way and you prove the other things. Okay, so let's say that I have a Taylor series like this, right? Again, right, I can just look for solutions in terms of the Taylor series, and now if I take the derivative, right, I get a1 plus a2 z, all right, plus, I'm missing a 2, plus 3, a3 z squared, and so on and so forth, n z n minus 1, right? And now if I would like these two things to be the same, right, then what do I need? I need a1 to be a0. I need 2a2 to be a1, and so on and so forth, right? In particular, I need n, right? I need this to be the same thing as an minus 1, right? And because I want the function to be 1 at 0, I also have that, a0 should be 1. And then if I work out what that means, right, I just get that. I mean, there's many ways of doing this, but I just get that the n is simply 1 over, this is not 1 over n factorial. Okay, and so in particular, this means that, the exponential of z okay, sometimes we write this as exp of z, right? It's just equal to 1 plus z factorial plus z squared 2 factorial. Right? And this is the Taylor series that you know from real analysis as well. Okay, so you can define exponential as a solution to this as the Taylor series. You can define it as cosine plus I sine, which just should show that sort of all these definitions are the same. Okay, I mean, right? I mean, if you have enough regularity, if the function is its derivative, then it would be also the same as its second derivative, and so on and so forth. Right, and so we know what the coefficients would have to be because of what we just showed in before I erased, and we would get exactly the same thing, right? Because all the derivatives at 0 are just 1. Okay, and so now we can ask, what is the radius of convergence of this? Okay, and if we go back to the Seville theorem that we did last week, we saw that, in order to see the radius of convergence, you just have to take 1 over the coefficient, right? 1 over the n, which in this case is n factorial, right? Because it's 1 over n factorial, and you just take the nth root of this, right? But as n goes to infinity, and you can see this from Stirling's formula, but you can also just think that you're multiplying the numbers from 1 to n, and then you're taking the nth root of this, right? It's not so hard to see that this should go to infinity, right? Because you're multiplying bigger and bigger numbers each time. Okay, and so this is going to infinity, right? And so the radius of convergence is infinity, right? So it converges everywhere. Okay, and now you can prove, right? The nice formula is that we use all the time for the exponential, right? That if I have e of a plus b, that this is the same thing as e of a times e of b, right? This is sometimes known as the product formula or addition formula, I think. Yeah, addition formula. Okay, you can do that directly from, I mean, now there's many ways. I haven't convinced you yet that this is actually true, although now you can do it, right, by just looking at the Taylor series of the cosine and sine. We'll do that in a second. But now to prove this addition function, we could try, let's say that we already believe this is true, right? Then we actually did that at some point, right? Because we took the product of two of these things and we saw that it was the cosine for the sum, at least when the input of the exponential was a purely imaginary number. Okay, but let's do it straight from the differential equation. Oh, I just saw there was a question. Yeah, if every function has a series. No, so right, if you remember over the reals, it's not at all true that every function has a series, as a Taylor series. In particular, even very smooth functions might not have a Taylor series. Right? There's functions that are smooth, are C infinity, but they still do not match their Taylor series over the reals. But over the complex numbers, this won't happen. Right? So over the complex numbers being differentiable, it will be a lot stronger, and we'll see that we'll force it to have a Taylor series as long as it's differentiable in a big enough place, right? In a neighborhood. Okay. Okay, so how do we prove something like this? Let's prove it straight from the differential equation. All right, so let's take the derivative of c. Let's say c is a constant, right? So I'm taking the derivative with respect to z of this. Right? I would like to show that as I vary z, that the derivative of this is 0. Right? Because it should be. If this formula holds, then then this should be e to the c. Right? So let's see. Okay, so I can now use I can take the derivative here, right? So I'm proving this formula using only the differential equation, right? This is the derivative of e c minus z times e of z plus e c minus z times the derivative of v of z. Okay, but now, right? What is this, because the derivative of e of z, right? We define e of z to be the function whose derivative is itself. So this is equal to e of z, right? On the other hand, here, right? What is the derivative of this? I have to differentiate this inside part, so it's minus, and then is the derivative of e, right? But that's again the same thing as e, so I get c minus z, right? And I pick up the minus sign because of the minus sign inside, right? Just change the rule. And so what I get is minus e c minus z e z plus exactly the same thing, right? So this is equal to 0. Okay, so this derivative is 0, and also, right, if I take this for z equals 0, right, I get that this, if I can do it, right, if I replace it at z equals 0, then this is equal to, right, e to the c, this function here, times z is 0, right? But e0 I know is 1, so this is e to the c, right? So as a function of z, I see that, right, it's differentiable, right? It's differentiable everywhere in the way that it was defined. And now, for z equals 0 is e to the c, and the derivative is always 0, so this must always be e to the c, right? So, I mean, there's many ways of showing this, but so e to the c minus z, e to the z needs to be equal to e to the c, right? And effectively, we've proved this addition formula. Okay, you could also you could also write out the Taylor expansion and just try to prove it on the Taylor expansion. I mean, it would be maybe not the nicest exercise to do, but you could definitely do it just straight out of the Taylor expansion too. So, sounds like not a great exercise, but okay. So let's see what else we can show about this. Maybe I'll leave this on the board. Oh, should have left the series. Okay. Okay, let me write the series again. I think it will be useful. E, X or Z, maybe let me use Z. More clear that it's a complex number, equal to 1 plus Z plus 1 half Z squared plus 1, 3 factorial Z cubed. Okay, so what can we immediately get? And we know also, let's write again the product formula, that A plus B is equal to EA times EB. Okay, so immediately get some things out of this, because if I just replace A and B by Z and minus Z, right, I get that E of Z, or let's say, let me do Z, and let's say that I take Z and minus Z, right? So this is E of 0 is 1. This is equal to E of Z and E of minus Z. So what can I learn from this already? Right, I learn immediately that the exponential is never 0, right? E of Z is never going to be 0, right? Because if it was 0, then, E minus Z wouldn't, I couldn't get 0 times something being 1. Okay, so it's never 0. Okay, what else can we get out of this straight away? Well, let's say that we take X to be real, right? Then if X is positive, or even bigger or equal than 0, right, it's not so hard to see that E of X, right, if you replace, it's going to be 1 plus something that's positive. Right, so E of X is bigger than 1, or bigger or equal than 1, say. Let's say that I take it bigger than 0, then it's bigger than 1, right? Because I get 1 plus something that's positive. So in particular, what this gives me right away, right, is that, again, because I have E of 0, which is 1, is equal to E of X, E of minus X. Since this one is bigger than 1, I know that this one must be smaller than 1, right? So E of minus X needs to be smaller than 1. Okay, I mean, these are all things that I'm sure you remember from real analysis, right? Because, because these coefficients, right, all these coefficients in this series are real, right? Since all the coefficients are real, if I take the conjugate, if I take E of Z conjugate, okay, maybe I'll use the word exponential instead to make it clear where the conjugate is happening, right? If I take exponential of Z conjugate, right? I get a conjugate on the Z. The conjugate can come out of the product, right? And then And then because this is real, this is the same thing as the conjugate. All the coefficients are the same thing as the conjugate, so I can put another conjugate, which means I can take now the conjugate to the top of the product, and then I can take the conjugate on the outside of the sum, right? So in particular, this means that exponential of the conjugate of z is just the exponential of z all conjugate. Okay, so what does this tell me? So let's say that I take y real, right? We're just sort of deriving, one by one properties of the exponential. And in the end, we'll derive sort of what the exponential really is, and all these properties will become sort of obvious. But it's a good exercise to just, see how by defining it as some solution of something, you can actually start getting all these. And this will be how we're actually going to define the cosine and sine for complex numbers. Okay, so let's look. Okay, so if we haven't yet, right? We haven't yet established this formula. But if this formula is to be true, then if I replace x by just a real number, right, which is what I'm doing here, then this is cosine of an angle plus I sine of an angle. So it better be that once I take the absolute value square, this better be 1, right? Because this number, right, is for sure norm 1. Right, and in fact, okay, what is this equal to? This is equal to e to the I y, e to the y conjugate, right? Because it's just the modulo square is the number times the number conjugate. But now I can move the conjugate inside, right? So if I move the conjugate inside, I just get minus I y, and this is just equal to a number, right, times its inverse is just 1, right? Another way to see this, well, okay, we don't quite know that this is the inverse, but we know that this is e to the iy minus iy. It's e to the 0 is equal to 1. Okay, so the norm of this is 1, so that's good. Moreover, if we have, say, now x and y both reals, let's see what e to the x plus iy is, right, in absolute value, say. Right? This is just the absolute value of Vx, right? It's the absolute value of the products, but that's the product of the absolute values. We also saw that. Y. So this is just equal to, like, this is 1. This is always positive. We know that the exponential the exponential of a real number is always positive. And so we just get e to the x. Okay, so we have the exponential of a complex number. Basically, the real part tells us its size, and the complex part is going to tell us its angle. Okay, so we'll get there in a second, right? And now we can define, right? Because right, what I sort of argued, or just told you, but I haven't argued, is that when x is real, right, an angle, then this is going to be true. But this is actually true always, and we're going to define cosine and sine of a complex number, which we haven't done before, exactly via this formula. Right? So how can we do this? We just define cosine of z, right, as e to the, right, e to the I z right? If we do this, then, okay, and I should define sine too. Two. Okay, so this can be the definition of the trigonometric functions for, over the complex plane, and we have to argue that these are actually, that these are consistent. Okay. Right, and it's clear if I multiply this by I, the I goes away, and if I add, I get exactly twice this over 2, I get exactly e to the iz. Okay, let me erase. Right, and now if this formula is to hold, I can just replace x by minus x, right? And it gets, we know that inside the sign, the minus comes out, and you get, okay, so let's do this. Okay. I want to keep what I can on the board, what I need. Okay, so I think I want to keep this. Okay, so e to the z. Right, and now if we work out what, okay, so now you can work out what the series for cosine and sine are, right? You just need to expand the series for e to the iz and the series for e to the minus iz, right? So we just replace z by either iz or minus iz, right? And we just have to work out what these are. Okay, so I'll just write them down. Okay, so we get cosine. Okay, so if you do that, right, you get the term, right? You get a bunch of terms with iz, a bunch of terms with minus iz, and now you add them, right? The odd terms, they will have a plus sign here and a minus sign there, so they'll cancel out. You only get the even terms, and indeed, if you work this out, which I mean, there's no, we just take time. There's no point to do here. Minus, right? And the plus and the minus are just because of the I, right? Okay, I mean, without working this out, should still be clear why something like this arises, right? Because if I replace the term, that sum here, inside by iz, and by minus iz, and then I add, right? Because one of them has a plus sign, the other has a minus sign. Anything with an odd term, right? The minus will come out, right? Because it gets minus 1 to some odd term. It won't come out in the other one, so any odd term will disappear because it will cancel out. And any even term will have an I coming out to I to that power, right? And so I to the power 0 is 1, I to the power 2 is minus 1, I to the power 4 will be 1, and then will be minus 1 and plus 1, and that's why this sum is alternating, right? I mean, it's something worth just doing, but it's the kind of thing that if you do it yourself and see what happens is more useful than me just working it out on the board. Okay, for the sign is exactly the opposite because of the minus sign, right, is exactly the odd terms that survive. And because it's the odd terms that survive, they'll all have an I, but we're dividing by 2i, right? So this is going to cancel out the I. Okay, so 3, sorry, right? And plus z5. 5, and minus z7, and so on and so forth. Okay, so these are the series. All right, and now you can just check. I mean, right, also you could just check straight here that indeed with the cosine and sine defined this way, that Euler's formula gets satisfied, right? If I take this plus I times this, I get this plus this. These terms cancel out. I get this twice over 2, right? And now this is one way of verifying that, you know, these are actually the sine and cosine that we know from real analysis. Okay, so this is all, I mean, this all feels a bit tautological because we sort of knew what was going to happen in the end. But, right, this gives you quite nice things, right? Because if you think about it, if you take, say you take x to be real, right? then we know that e to the I, or let me say y, because we've been using y for imaginary part, just to be more graphic, right? We know that this is 1, right? We just proved that like 5 minutes ago, right? Because the same as e to the high y times e to the minus iy, so this is 1. But, right, what is this? Because of that formula, it's just exactly that, right? It's the norm of cosine of x, of y, plus I sine of y. Right, but what is the modulos? The modulo square is just, the real part square plus the imaginary part square. So this is cosine square of y plus sine square of y. Right, so immediately get, the formula, important formula in trigonometry, that cosine square plus sine square is equal to 1. Right? You get also immediately other things, like if I have, say, y1 and y2 reals, right? Then having e to the, okay, let me write it this way, e to the I, say y1 plus y2, right? This is equal to e to the y1 to the I y1 times e to the I y2. But now if we look at what this is, right, this is just a cosine of y1 plus sine plus I sine of y2, sorry, y1 times cosine of y2 plus I sine of y2, right? And now, right, okay, so we have this, but on the other hand, this is equal to just cosine of y1 plus y2 plus I sine of y1 plus y2, right? And so immediately get this, the addition formula for the trigonometric functions, right? Because cosine of y1 plus y2 will just be the real part of this, right? Which is this times this minus this times that. So if you ever forget the addition formulas for the trigonometric functions, all you have to remember is this way of defining sine and cosine, or, I mean, equivalently, just this formula, which seems a lot nicer. And then you can basically work out all those things from this, right? You can also very easily work out, I mean, things that are not, they're not that obvious if you, the first time you think about it, but things like, oh, this is done, right? Things like the derivative, right? The derivative of cosine, right? The derivative of cosine of z is equal to minus sine of z. Right, this formula is you probably remember from trigonometry, and the derivative of sine of z is equal to cosine of z. Right, this all comes out straight away if you just plug in these formulas. Right, so a lot of things about in trigonometry actually come straight away from this formula and from just the property that the exponential of the sum is the product of the exponentials. Right, and so now, I mean, in particular, the very famous, right? If you look at this formula, maybe this can't see this so well here, right? If you look at this formula and you replace x with pi, right? Then you get that e to the I pi, right, is equal to cosine of pi, which is minus 1, right? Because you go all the way to the other side, right? So you go here. And sine of pi, which is 0, so you get that this is equal to minus 1, or in particular, that this plus 1 is 0. Right, and this is known as one of the, argued to be the prettiest formula in math because it uses, 1, I, and pi, and e, and it sort of feels very mysterious, but now it's kind of clear what it means, or why it's true. Right, and maybe one thing just before we finish, and then we'll talk a little bit about the logarithm, is that, right, what we're seeing, we understand very well now exponentials of real numbers and exponentials of purely imaginary numbers. And so this means simply that if I have e to the x plus iy, right, let's say x and y are both reals, then this is just e of x, right, which is a positive number. This is like this is a positive number. times cosine of y, right, which is an angle, plus I sine of y, right? And this is an angle. I mean, an angle in the sense that it's a norm 1 vector. Let me just write it this way. Right? And so these are effectively polar coordinates. Right? These are just polar coordinates. And we'll talk a bit more about this. Right? Because this is like a radius. And this can be characterized by an angle. And in particular, usually write this way. Right? So we tend to write, when we write in polar coordinates, we write r, which is a positive or non-negative number, which is just the angle times the radius times the angle. Right? And this is so useful. I mean, many times we write numbers this way. Right? Where theta is the angle of the number. Right? This is theta. And this is the distance r. Right? And the exponential will allow us to write things like this. Right? And so what we're going to do after the break is, given a number, you're going to be interested in knowing what its angle is and what its radius is and so on. So we have to figure out how to invert the exponential. Right? We all know that this is given by the logarithm. But of course, there's going to be issues, right? Because this is an angle, but if I add 2 pi and go around, it's still an angle. And if I add 4 pi and go around twice, it's still an angle, and so on. And this is going to create some difficulties that we'll explore after the break.